So it's a pleasure to have Lampros, and he's going to talk about inside the hologram. So please, thank you, Lampros.
All right, well, thank you for having me here. It's a pleasure. So I imagine all of you will be watching the debate later. So I hope this will be somewhat more informative. And I don't know whether it's going to be more entertaining, but yeah. All right, so this is work I recently completed with Daniel Jafferis. And the question is, how can we see the hologram? How can we see from inside the hologram, from the perspective of a bulk observer in ADS-CFT? Now, taking this, switching to this perspective, to this reference frame of an internal subsystem of a quantum theory is interesting on its own sake, but it's particularly motivated by the question of the black hole interior. So the question there is, okay, how can we probe the structure, what happens behind the black hole horizon? This could be a single-sided black hole formed from collapse, or it could be a two-sided black hole like the one I drew here in this figure. And the problem with black hole interiors is that if you try to probe it, you would have to necessarily send something inside, but you know that classically this will never come back out, and quantum mechanically, when it does, it will be too late and it will be very scrambled. Yet if one of you decides to get on a spaceship and go to the center of the galaxy and fall into that black hole, you will definitely experience something. And this is not metaphysics, it's an operationally well-defined question. What did you encounter once you crossed the horizon? From your perspective, you will cross the horizon at finite proper time. So it's reasonable to try to address the question, even pose the question, of how would we compute from the CFT certain aspects of the experience of the infalling observer, like for example, the proper time that they computed, that their clock measured until, let's say, they hit the singularity, or they met some other observer that fell in earlier, and so on. Of course, a related question is, did they encounter any particles after crossing the horizon? If they're carrying a Geiger counter, did it click? And a more refined question, of course, is how can we reconstruct the operators that this observer can couple their devices to? Somehow the dynamics of this evolution along this borderline allows the observer to access certain CFT operators that they can measure and excite. So the question is, well, what are these operators? Can we have some sort of understanding of what degrees of freedom become available to that guy after they cross the horizon? All right, so of course the framework will be ADS-CFT, where we have some understanding of both the semi-classical description of the physics and the microscopics. But the problem with ADS-CFT in its understood formalism is that it describes the black hole completely, we assume, but from an asymptotic reference frame. So from the perspective of an observer out here at infinity. And from that distance, the black hole looks like an ordinary thermal quantum system, which various properties of which we have understood sufficiently well. It has a finite entropy, which we can count in certain contexts. It has fast scrambling dynamics. And of course, the evolution is unitary. But the issue is that this description doesn't really make an explicit use of the interior part of the black hole. What we interpret in the gravitational part of this story, in the gravitational dual, as the interior. And roughly the issue is that, semi-classically, the CFT evolution can be thought of as generating this kind of Schwarzschild time, which only asymptotes to the future horizon at t goes to plus infinity. So in a sense, not a very precise sense, but in a sense, the black hole interior is kind of in the future of the CFT evolution. Of course, the CFT is expected to describe everything that some kind of infalling probe experiences, but it's difficult to square this with the expectation of general relativity that kind of tells us that there's a nice kind of extension of the space-time behind the horizon, and the probe will, at least for some time, will experience this propagation in some more or less vanilla space-time. The way these two are supposed to go together go by the name complementarity. And the idea is that there is an equivalence between two different descriptions. There is a purely exterior description, what the CFT provides. From which perspective? Yes, sure, yeah.
sorry, you're drawing, I think, a two-sided black hole, but if I could ask a question just about a one-sided black hole, like the one in the center of the galaxy, I'm a little bit confused by the statement on the previous slide where you say that the CFT only describes the exterior of the black hole because the entanglement wedge would certainly include the interior.
Yes, that's right. So first of all, right. So there's two different type of setups that one may consider. Two-sided black holes, single-sided black holes. We will be mostly focusing on two-sided. We will kind of not focus on black holes for most of this talk, and we'll get back to that question towards the end. For the case of the single-sided black hole, it's true that the CFT we expect provides a complete description of the experience of the infalling observer. The statement I'm trying to make here is that this use of this part of the evolution is the evolution that corresponds in the semi-classical picture to the propagation in the interior is not it's not explicit in the CFT. It's not we don't exactly, I think we will agree that we don't exactly know. We understand fairly well how to describe how to connect the CFT dynamics to the exterior physics of the black hole. But once the excitation scrambles, then we don't have good understanding of how to reconstruct the experience behind the horizon. That's kind of the issue I'm trying to illustrate. Is this? So yes, I was actually about to make a comment of exactly along these lines. The CFT, of course, is supposed to describe, to provide a full description of the experience of some infalling probe, but it's in a very different language than the language that the infalling observer themselves would use. And the idea is that complementarity allows us to somehow reorganize the physics of the CFT that describes this infalling probe in some other way that allows us to connect with this GR expectation under certain circumstances. We don't expect the GR expectation is a generic fact, but we would like to understand under what conditions this GR expectation is well motivated and can be used for describing the physics of the infalling probe.
If I had considered a situation that doesn't involve black holes, but where the entanglement wedge is larger than the causal wedge for some other reason, would you still say that the way that we would construct operators in the region of the entanglement wedge that's outside the causal wedge is related to complementarity? In other words, are you saying that there's a difference between the case where I want to reach beyond the causal wedge?
No, I don't think there's a fundamental difference between the two. I think the abstraction in reconstructing the physics behind the horizon of a single-sided black hole and behind the causal wedge in the setup that you suggested, I think it's probably analogous. I can't be 100% sure. They seem to me a similar type of problem. But in both cases, there is a complementary description of the physics, right? There exists a description of the physics from the perspective of the infalling probe. There exists a reference frame of the observer. The observer themselves will register something. They will have their own kind of organization of their physics. There exists some kind of Hamiltonian, right, that propagates, that evolves along the observer's borderline. This is not independent data. The experience of the infalling probe is entirely contained within the boundary CFT description, but there is some way that we can reorganize this information and derive a Hamiltonian for propagating along an observer's borderline. And we would like to understand what are the principles for this, that underlie the derivation of this H. So the goal is that there exists some sort of physical principle, which we haven't exactly pinned down yet, that allows us to switch reference frames from the CFT reference frame, the asymptotic frame, to the reference frame of an observer that propagates in the bulk. And this will be some kind of different approach to the problem of reconstruction of the interior of the hologram, and the interior of the black hole in this kind of figure I drew. The point I want to emphasize is that we're not allowed to choose what this Hamiltonian is. This is determined, this is kind of enforced by the physics of the CFT. Our goal is to discover what's the principle that gives us the right Hamiltonian, not to come up with it. So I think this is in line with your intuition, Raphael, that it's not independent information we're trying to, the observer of the experience of an observer traveling in the bulk, falling inside a black hole and so whatsoever, is entirely determined by the CFT physics. The question is how to extract it. And we would like to identify the physical principles that allow us to switch to the observer's reference frame. That's kind of the motivating goal of this work. Is the general question clear? We would like to identify the principles that that will allow us to construct these Hamiltonians that allow us to propagate along arbitrary word lengths. That's kind of the goal. In fact, I would like to kind of mention a puzzle which is associated to a two-sided black hole, which we won't address until the very end. So here's it's not a paradox, but it's a puzzle. So here we have a two-sided black hole, and we know that this is described by two CFTs, which are decoupled. There's a left CFT and a right CFT, and the two of them are decoupled, but they are in a highly entangled state, which we call the Thermofield double state. Now, of course, it's possible for me to act with an operator on the right CFT and create some sort of coherent localized wave packet, which, according to the expectation from GR, it will, after a finite proper time, will just cross the horizon. Now, because of the two CFTs being decoupled, the observer, the excitation I created, which is an operator in the right CFT, commutes at all times with the algebra of operators in the left CFT. However, after a finite proper time, clearly I will, according to this picture, I'm expecting to be behind the horizon, which would allow me to receive signals from the other side. And this means that after some finite amount of proper time evolution, I expect the operator that describes my excitation to be not just to belong on the union of the two algebras, not just on CFT right. So whatever the physical principle is that allows us to switch to the reference frame of the infalling observer, to the reference frame of that probe, it has to give rise to an appropriate coupling between right CFT and left CFT. Even though there's no dynamical coupling between the two, whatever principle allows us to switch reference frames has to do that for us.
Sorry, question. But in this case, time evolution has to involve both, right? Because it's just...
The time evolution here, it involves both, but it doesn't couple the two. I'm sorry, the CFT evolution doesn't couple.
No CFT operation. I'm saying that infalling time evolution is simply just left plus right dagger plus just usual both. Absolutely.
Whatever this Hamiltonian here that propagates in proper time is, it'll have to involve both. You'll have to couple CFT right and CFT left. But we're not in kind of, to emphasize the point I was trying to make earlier, this Hamiltonian is something to be derived, right? It's something that we're not allowed to just choose a coupling between the two sides and just evolve with this, with changing the physics. We expect that, so we would like to identify the physical principle that allows us to switch reference frames, and by doing so, a coupling will be generated in the situations where there exists a common interior.
Yeah, of course you can do whatever the time evolution you want, but of course a useful one is clearly limited, associated with the free fall frame and so on and blah blah blah.
Well, I think that we will agree that if you were an observer in this type of setup, jumping in from the right, you don't really have the freedom to choose how, what you will encounter once you cross the horizon, right?
Yeah.
Your future is determined by the dynamics of the two CFTs, at least as long as we believe that they provide a complete description.
Mm-hmm.
So So you're not allowed to choose what this proper time Hamiltonian is. It'll have to be something to be determined. And in this context, I'm just kind of pointing out a somewhat puzzling feature, that this principle that will give us this Hamiltonian evolution will necessarily have to involve both sides under certain conditions, whenever there exists such a common interior.
Yeah, I totally agree. Yes.
Oh, okay. Yeah. So
Yeah,
we will have to understand under what conditions such a coupling arises.
Yeah,
so.
good. Only thing I said is that it need not be a proper time associated with the geodesics. Of course, you can describe things in a different frames and so on, and just anything is fine. And I mean, as long as you extract the physics in the right way at the end.
Yeah. Okay. So I guess my question is, how do you extract the physics? How do you extract the physics that a semi-classical observer would expect to see? Okay, so this may be getting a little philosophical, but yes, please.
Sorry. There's something a little, well, there's something certainly ambitious and I think more complicated about discussing specifically the experience of an observer rather than just local operators in the bulk. I mean, for example, this observer that you're drawing isn't really a closed system, right? As is illustrated by the fact that something might be coming from the left boundary and hit it, and that something only enters the observer's past light cone at some finite time after they started. And so, you know, the description of such systems is I think intrinsically more complicated. But if I just asked about an operator at some point on that world line, then I would have just said, well, you know, before the world line crosses the horizon, you know, that operator is in the entanglement wedge of the right CFT, and after the world line crosses the horizon, it isn't, but it is in the entanglement wedge of the two CFTs, and that's the answer to the question of why we need the second CFT.
Right. But let me take that as I use this as my jumping off point and mention the following: that we would like to understand in a kind of a dynamical way in what sense this discontinuity happens, right? So I think there's a physical question here that is relevant. This guy, we agree that I can create an observer by simply never touching the left CFT. And this guy will propagate in a particular way. And the operators that this observer can couple their devices to, up until that point in the semi-classical evolution, right before they cross the horizon in their proper time evolution, are entirely right CFT operators, but immediately after they cross the horizon, as you say, the entanglement wedge changes, and now there's a different, I can't describe the observables that this guy can measure anymore in the original CFT, but now I have to involve both sides. So we would like to understand, at least it has been a puzzle for me, that we would like to understand dynamically how this discontinuity happens. In what sense you as an observer, the observables that you can manipulate changes in that discontinuous way after you cross the horizon.
I still don't really understand. From the discontinuity that you are discussing refers to the boundary theory.
Yeah, that's right.
Usually I don't need the left theory, and then eventually I do, but why is there a discontinuity in the observer's description from their point of view?
From their point of view, there isn't any. In the CFT there is. So we would like to understand in what sense these two go together. Let me put it in a kind of more practical way. Under what conditions does the observer receive is the observer able to receive something from the other side? You know, I could have a short wormhole, or I could have a long wormhole, in which case I can't receive something from the other side. So
this discontinuity is just a result of your choice of boundary Hamiltonian. You just chose a Hamiltonian in such a way that the time infinity corresponds to this horizon. So that's why, of course, using that evolution, you don't see it.
That's right. Yeah, I would like to see. That's kind of the question. In fact, actually, okay. So the problem with the issue that we're facing here is that I think that I need to make what I'm saying a little bit more concrete in order to provide the basis for this discussion. This was a part of motivation. I think there's a question here. What would break if we concluded from this puzzle that an observer made of matter from the right could not receive signals from the left? Well, what would break is I guess the ER equals EPR statement, the statement that there exists some sort of semi-classical interior in certain wormhole microstate, black hole microstates of this type. That there exists certain states in which the semi-classical expectation that an interior exists and it's operationally meaningful, that will break down. Now, okay, this may turn out to be the answer, but I don't think that we believe that is the answer, and I will argue that it is not.
Sorry, can I also ask a question if you don't mind? So this fact that the infalling observer and the left signal can meet each other, is you can see it in the bulk and Kruskal time evolution, right?
You can see it in the bulk, say again?
Yeah, using Kruskal time evolution.
Yes, that's right. In the bulk, there's no mystery. It should be, to the extent that you can use the extension of the black hole geometry in the interior, there's no mystery, of course. You can just switch coordinate systems. The question is, we would like to understand how to switch reference frames from the CFT perspective, directly on the quantum mechanical system, and kind of see under what conditions such an interior does exist, under what conditions I do receive a signal or I don't receive a signal.
Right. Sorry, I was, what I wanted to ask was, so the Kruskal time evolution, I believe that if you work out the Hamiltonian for that, it turns out to be h left plus h right.
That can't be correct though, right? Because h left plus h right doesn't couple left and right.
Yeah, that's what's confusing me. I thought it turned out to be that. Am I just wrong?
Okay, so all right, so hold on to that thought until the very end of this talk, where we will get back to black holes. So for now, okay, let me now be a little clear. So what this is supposed to motivate this discussion, and but now we're gonna switch gears to a setup that is much less conceptually confusing and more clear, and present a framework for extracting the experience of an observer inside the bulk directly from CFT data. So that's what we're gonna do. It's gonna be more ordinary bulk reconstruction, and then we're gonna use the lessons we learned along the way at the very end to gain some insight into the experience of this infalling observer. So we will get back to black holes, but at the end, once we have kind of established some common ground. The questions I'm asking, in a sense, can also be seen at the level of ordinary bulk reconstruction. You know, all the reconstructions you know and love, HKLL, modular flow reconstruction, PETS maps, and all that, require, at some level, they require input of the background solution in the bulk. That's a fact. And we would like to look for some sort of a universal prescription, something that doesn't, of course, it's going to have to use information about the CFT state that we're discussing, but we would like to find something that is formulated directly in the CFT without making use of the bulk, at least making more limited use of the bulk. That's kind of, it's another way of phrasing the motivation. Okay, so let's get to it. All right, so I'll spend a few minutes unpacking this slide, so you don't have to try to see what it says. So we would like to introduce some sort of observer into the system and somehow learn how to follow the observer's world line. But we're not trying to solve the hard problem of consciousness in ADS CFT. We're simply trying to construct some sort of universal and semi-classical probe that we can use. A nice universal semi-classical probe is a black hole. So our observer will be a black hole, in particular a black hole that is entangled with a reference system. The role of the reference system is, roughly speaking, to allow us to keep track of the frame of the black hole in the bulk. So the way we're going to do this is the following. So we start with two identical CFTs, and we start them in the Thermofield double state. We have the system and the reference. This describes, of course, just a static black hole in ADS on the system side, and nothing else is interesting there. But now what we're going to do is that we're going to act on that Thermofield double with a system unitary. This unitary in the system does kind of two jobs. The first job is to move the black hole out of the way on the original, let's call it t = 0 time slice. So we act with the ADS symmetries to translate the black hole far out towards the asymptotic boundary. And then the rest of that unitary, this unitary also then is responsible for generating some sort of semi-classical background, any sort of semi-classical background it likes, within some finite region of the ADS. We don't allow, it can also excite the fields. We don't allow the unitary to act very close to our black hole, which, as I said, we assume it's very far away in the initial slice. And we also don't allow this unitary to generate superpositions of classical geometries. We want to have a semi-classical spacetime. And then we evolve the system. And we call this state psi, and of course, it depends on time. And for as long as the size of the black hole is smaller than the features of the space-time that I created with this unitary, the black hole, by the equivalence principle, will simply propagate along the word line of the ideal observer. Now, okay, you may say, now you're justified to say, wait a minute, you're using a Thermofield double to introduce your black hole. This means you're using a canonical ensemble to describe your system black hole, which means your black hole is cosmological size, so it's not exactly a probe. So that's true, but it's not a fundamental restriction of what I'm about to say. There is a version of this story that uses a microcanonical version of this Thermofield double state, which allows us to make black holes that are parametrically smaller than LADS. I will leave this discussion for the end. For now, we'll be using this Thermofield double for convenience and clarity. All right, so is this setup clear?
Well, that depends on whether you insist that we wait until the end. I mean, I think this question of the size of the black hole is pretty important because indeed, if the black hole is at least an ADS radius in size, then I don't think this probe approximation is valid. And if we make it smaller, then would you expect that its wave function spreads out over about an ADS scale?
Right.
Pretty quickly?
Good. So, okay. So two questions. So, right. So there's a question of to what extent an ADS-sized black hole is a probe. Well, an LADS-sized black hole is a probe in a space-time, let's say, of a black hole which has 1,000 LADS scale radius. Or in a space-time where the features, the curvature perturbations about ADS is much larger than LADS. So in this sense, this is a probe for this probes the features of the space-time at super ADS scales. Now, the question of the microcanonical version of this description, yes, so this is true when you...
But I don't agree with that statement.
Okay.
I mean, I don't understand how you can claim that something is a probe that's larger than the curvature scale of the background that you're probing. I don't think it matters whether or not you have a black hole there that is very big. I mean, even an empty ADS, it just wouldn't be a probe. It significantly changes the solution.
I am simply saying that if in fact, this is a statement that this statement is something that I can explicitly show you later on, that what I'm about to say describes the physics of black holes moving in pure ADS, and by extension, it can also be shown that they describe black holes that propagate in weak curvature perturbations of pure ADS, namely perturbations that change the curvature of the spacetime at scales larger than the curvature of ADS. So this is a statement that I can substantiate. So in that sense, if you understand how this probe works in pure ADS, and you also understand, then any curvature perturbation that affects the structure of the spacetime at scales larger than LADS, then from that perspective, your ADS black hole is a probe in the new perturbed spacetime.
I mean, there's many ways that we could try to characterize this, but one of them would be to ask, what is the light crossing time of your probe? And, it's LADS, right, at least. And that's the same time that, I mean, the time that this probe will spend in the space-time, if it's falling into a large ADS black hole, is less than that. So the probe can't even communicate with itself in the time that it takes for it to fall into the black hole.
It can communicate with itself.
Yeah.
I can definitely propagate degree operators along this probe's trajectory. I mean,
what I mean is that one end of the black hole that you're throwing in can't talk to the other. It takes at least a time LADS to send a signal from one end of the black hole to the other.
Right, but
it's a longer time than it takes for that black hole to fall into the bigger one that you're throwing it into.
Right, but this will not be a restriction to what we're about to do. I understand what you're saying. This process of trying to bring in contact the two antipodal points of the black hole will not be of relevance for our purposes here. So I don't want to go into the microcanonical black hole discussion right now because there's lots of ground to cover, and I would like to leave this discussion at the end. I agree the spreading of the wave function is something that one needs to be careful about, and we discuss it in our paper carefully. Let's get back to this in the end, if you don't mind, Raphael, so that I can actually make some progress on the formalism. But I hope that at least we agree that for certain purposes, this black hole can be a probe. If not, let's move on and we can get back to this at the end. By the way, I don't know how strict you are with time. So, okay, I don't know what that head movement means, but
that's how much you're interrupted.
Okay, all right. Keep interrupting then, because there's lots of stuff to say. All right, so okay, so this was the setup, right? This is how we introduce an observer into our system, and now I want to introduce two concepts that will be of relevance for actually, saying something about this. So the first one is the modular Hamiltonian of the black hole, of the system. And what I mean is the modular Hamiltonian that the system has after I trace out the reference. So we had a global state that describes reference and system, and I'm tracing out the reference, so I obtain a density matrix for the system. I'm sure you're all familiar with this, but I have to go through this. And the modular Hamiltonian is minus the logarithm of the density matrix of the system, roughly speaking. And in this setup that we are using, the modular Hamiltonian will be at all times, at all CFT times, will be unitarily equivalent to the CFT Hamiltonian, simply because we acted with a unitary on top of the thermofield double. The thermofield double, the modular Hamiltonian in the thermofield double is just the Hamiltonian, and the application of the unitary simply conjugates H. So this is the first concept we will make heavy use of. And I can already kind of give you some early intuition for why this object would be useful in the discussion of proper time evolution of along the black hole's trajectory. It won't be a solid argument, but it's some intuition to keep us going. So we constructed the state of our observer into the system by starting with a thermofield double, which you may know or you may easily confirm that is annihilated by the difference of the Hamiltonian of the reference system and the system. This means that the boundary time of our reference is correlated with the boundary time of our system, which is of course simply the time in the frame of the black hole. It's the proper time measured by the black hole because it's a static black hole at the center of ADS. But after I apply the unitary and time evolve, the new state, psi of t, is now annihilated by the difference between the reference Hamiltonian and the modular Hamiltonian on the system side. So now you see that the same quantity on the reference, the clock on the reference, is now correlated not with the dynamical clock of the CFT, but with the modular clock. So this kind of gives you an early idea, an early hint that perhaps the natural internal clock for the black hole should be associated on the system side with its modular Hamiltonian. So we will try to flesh this out more concretely later on, but it's good to have this in your mind.
Sorry?
Yes.
In the expression you've written down, sure, the e power IHTs, is this the Hamiltonian of the probe black hole or the Hamiltonian of the probe black hole plus the ambient spacetime?
So I didn't fully hear the question. This H, so here I'm referring to the modular Hamiltonian on the system side. The modular Hamiltonian on the reference side is always H reference because we never touch the reference. It's there, you know, for
right. But the system is inside another ADS spacetime, right?
Yeah, that's the modular Hamiltonian that I obtain after I start with a global state between reference and system, and I trace out the reference, and I obtain a modular Hamiltonian for the entire system. Okay.
Oh, I see. So the ambient space-time that the probe is moving around in.
Yeah. So this is the modular Hamiltonian for my entire system CFT.
Okay, thank you.
All right. So this is concept number one, and there's a second concept that I will use, and I want to be a little careful in discussing this. So the observer has a certain set of degrees of freedom they can manipulate. And this has to be operators that live in the vicinity of our probe, in some kind of atmosphere around the black hole. In the figure I was using earlier, I'm thinking of the observables that the observer can manipulate as some localized operators within some sort of neighborhood of my black hole within this kind of green tube. The size of this atmosphere is not, it's not some sharp boundary, but it's something that has to be, comparable to the size of the black hole, but not much bigger. Now, of course, we don't want to have access to the observables. We don't want to input the observables that the observer can manipulate, because that's kind of inputting the answer we're trying to find. However, we would like to, at this formulation of the setup, we would like to have access to these atmosphere operators at the initial and the final moment. So a physical way of thinking about this is as introducing a black hole somewhere near the boundary, as I said. There's various things happening in the middle of the space-time. The black hole propagates through everything and then goes back out towards the asymptotic region at some later time. And at that later time, we assume that we regain control of our system. So we can, again, reconstruct from the CFT. We have knowledge of the CFT representation of the local fields in this atmosphere of the black hole. This would be an input into our setup. Of course, the unitary that relates the initial and the final atmosphere operators will, of course, be, by definition, the proper time evolution. But at this level, it's just some abstract unitary, kind of a black box in the CFT. I have access to the early atmosphere operators, the late atmosphere operators, and some unitary relates them. What the goal of the rest of the talk is to input these three objects we mentioned, the CFT Hamiltonian, the black hole modular Hamiltonian, and this unitary V that relates early and final atmosphere operators, and learn something about what the probe experienced. In particular, how much time passed in their reference frame and how much energy they detected along the way. This will be the goal for the rest in the setup. Of course, ultimately one wants to upgrade the setup even further and somehow, remove the requirement of having access to the final operators. But this is what we will focus on at this talk, and we'll discuss possibilities for doing better. Is the setup and destination clear? I should pause a little bit for questions, because now I'm going to describe the formalism.
So I guess I have a question, which is, there seems to be some approximation involved here, where you're assuming that the black hole is a system that doesn't sort of scramble with the rest of the environment in the space-time. Like, for example, if I had, so I like it certainly makes sense to try to tag your probe by entangling it with a reference system. So, so that way you sort of know which degrees of freedom are your probe, even once it's gone into the space-time. That's really cool. But suppose that your probe had been a bunch of particles that decay or something. And so very quickly, you know, they spread out of the rest of the space-time, they get scrambled in with other degrees of freedom. At this point, they're just logical operators in some sense that have no interpretation as, you know, physical particles propagating through the space-time. Are you, now clearly in principle, this is something that could happen to the, you know, to the atmosphere of a black hole as well. I can certainly entangle a particle with a degree of freedom in the atmosphere of a black hole. But are you assuming here that that doesn't happen?
Good. So, all right. So okay, first of all, this issue of a particle's wave packet spreading and potentially scattering off of other things and getting entangled with everything is the primary reason why we use the black hole. So, of course, it's not the easiest probe to introduce into the system, but it's a well-behaved one. So, okay. So we are making the assumption that we have the setup is that whatever unitary you applied on your Thermofield double created a semi-classical spacetime with perturbative excitations on top of it, which may fall into a black hole. So our black hole is allowed to absorb energy along the way, but it has to be perturbative amount. So it has to be a small amount. It should not scale with, it should not be comparable to the mass of the probe black hole. And the nice thing about black holes that we're going to see a little bit later is that it has a black hole has a universal response to detection of a particle. It simply grows a little fatter. And that would be important in order to detect, you know, in order to reconstruct how much energy I kind of absorbed along the way. So yes, of course, you could imagine much more like elaborate, you know, situations that could cause problems. But I think within this class of states that I'm discussing, this issue doesn't arise in this case. The wave packet of the black hole doesn't spread, and if something crosses paths with the black hole, it will just get absorbed. Namely, everything that will happen in the atmosphere will eventually decay in time due to the quasi-normal mode decay, and that is an important aspect of this formalism. So I want to make one last comment on these atmosphere fields. These are operators in a gravitational theory. So I have to be a little bit more precise about how I frame them, how I address them. How do I determine this location X at which I'm putting it? So we're interested in describing observables in the reference frame of the probe. The probe, as I said, is a black hole propagating in a space-time that has structure at scales longer than the radius of the black hole. So the neighborhood of the black hole is always locally ADS Schwarzschild. So I'm placing these operators at specific locations in this local ADS Schwarzschild frame. The same way that, you know, if you had an ideal observer, there's a locally flat neighborhood around it, and you can dress operators, you know, with reference to the worldline in this way. So I'm always dressing these observables to the local horizon, the horizon at this particular point. Of course, I'm assuming some kind of, you know, I'm assuming that the horizon is, that we don't have a terribly dynamical situation. The black hole can absorb particles, but this happens at a slow rate and so on.
Lampros, I'm really confused. How do you know? Suppose that a particle has fallen into the black hole. At that point, the thing that your reference system is entangled with is just a subsystem of a larger black hole. And you know, the quantum evolution, I mean, it's true that the classical evolution is very simple, and you wouldn't expect anything dramatic to happen if the black hole was falling in a certain way before, you know, the particle fell in. The slightly bigger black hole will continue the same way. But once you start talking about operators like the atmosphere operators, I would expect those to depend very sensitively at least after one scrambling time, I would expect them to depend very sensitively. Are you working at timescales much less than one scrambling time?
All right, so two comments. So I will discuss what happens when particles fall inside a little bit later. So we'll get back to exactly how we describe it. The formalism is valid at most a scrambling time after the first particle fell in. So from the moment you observe, from the moment you absorb a particle, this formalism, at least at the level that we have developed it, is valid within a scrambling time from that. So that intuition is correct. So yes, because, right. Within that regime, let me give you some early intuition for why this is so. Within that regime, you know, within this time scale of a scrambling time from the absorption of the particle, the response of the black hole is effectively a Shapiro delay. And that's exactly why we can extract what happened, how much energy, whether energy was absorbed by our black hole. If you wait longer than the scrambling time, then it becomes more complicated, and I don't have precise things to say. So yes. All right, let's get to it. This is the entire talk. This slide is the entire talk. I will explain everything. This is the main formula. I'll go through it carefully, and then I'll try to explain as many of the things that I will mention now as I will have time to. All right, so first things first, what's the left-hand side? The left-hand side is the logarithm of this unitary V that relates our early and late time atmosphere operators, which we assume is an input. And the subscript H means that I'm doing so in the Heisenberg picture. This is the picture I'm using to represent my atmosphere operators in. All right, the right-hand side is an expansion, is a decomposition of this logarithm of V. And it's a decomposition in eigen operators of the modular Hamiltonian K at the original time slice. What eigenoperators mean, of course, it means what, you know, it means exactly what it sounds like. It's operators, let's call them G of lambda. Lambda is a subscript that, you know, after I commute it with the Hamiltonian, I get back the same operator times lambda. There are two interesting classes of eigenoperators that appear in this decomposition and are relevant for the two things that we want to probe. The first one is the operators with lambda equals 0. These are things that commute with K. That's why we call them the zero modes. And these are symmetries of the Hamiltonian, of the modular Hamiltonian, symmetries of the state. Of course, one of these symmetries is K itself, but there can be other zero modes, like for example, you know, rotations around the black hole will preserve the correlation functions of the atmosphere operators. So that's another symmetry. So the claim is that the coefficient of this modular Hamiltonian in this decomposition equals the proper time in thermal units, in units of the temperature. The coefficients of the other zero modes, of course, correspond to, you know, some amount of rotation that happened along the way and so on. We will not discuss this in detail because they kind of have they're very analogous to how the physics they're very analogous to the discussion of K0 itself. The other class of interesting eigenoperators are those that have an imaginary eigenvalue. In particular, imaginary with a positive imaginary part. These are things that grow exponentially under modular flow. These things exist. Modular Hamiltonian is an unbounded operator, so these things can exist. And Jan de Boer and I, following some insights of Tom Faulkner, Min Lee, and Huazhou Wang, argued that there is an upper bound on how big that imaginary part can be in situations like this. And the bound is that K squared needs to be smaller or equal to 2 pi in the canonical kind of normalization of K, of the modular operator. The thing that saturates that bound, we'll call them the scrambling mode. And it's this guy. Well, it's not a single operator, it's a class of operators that saturates this, and we call this and it's precisely this G of 2 pi. To give you some intuition of what this G is, if this was a static black hole and K was simply the Hamiltonian of the CFT, this guy would be an A operator at the horizon, a localized average null energy operator. And this commutator with an imaginary eigenvalue simply follows from the local Poincare algebra close to the horizon. The coefficient of this guy depends on the amount of energy that got absorbed along the way, the energy distribution. I can briefly mention the insight, and we'll the heuristics. Can give you some idea for why this is so, and I'll explain in more detail later on. The idea is that every time a particle gets absorbed by the black hole, what happens is that this the energy distribution of the infalling matter gets imprinted in the Shapiro delays that affect the propagation of the atmosphere operators to the future. So the effect of this scrambling mode contribution to this expansion is precisely to implement the right Shapiro delays that will allow us to propagate the original atmosphere operators to the late atmosphere operators. And that kind of brings us to the observation that that Raphael made a little bit too early, which was if I were to use that to go a little bit further in time, the relation between the late time observables and the early time observables wouldn't have that simple form given by this Shapiro delay. And we'll see that more explicitly later on. Everything else, besides the zero mode and the scrambling modes, everything else is bounced up into this term. Namely, they're either suppressed in 1 over n, or they are exponentially decaying in proper time, because they are transient effects that decay due to the quasi-normal modes of the black hole. The only 2 persistent effects that we claim are there are the zero mode and the scrambling mode contributions to this. All right, my goal is to explain what I just said in a little bit more detail from now on. I have no idea how much time, how long I've been speaking for. I've completely lost any sense of time. So how are we doing? Can you give me an estimate on how long you want to hear me talking still?
Well, I think normally, I mean, you know, I don't know. We can certainly you can certainly talk for 20 more minutes at least.
Okay, 20 minutes sounds good. Thanks.
Yeah.
I was hoping for that number. All right, so this is everything I'm going to say from now on. So any questions so far? All right. Good. Okay, let's try to be a little bit more precise now. So let's start with the case of no infalling particles. There are no particles that are bound to fall in our black hole in the original state. Our black hole will propagate undisturbed and come back out towards the asymptotic region. And in this case, we would like to understand what is this unitary V of H that relates the late time and the early time atmosphere operators that we mentioned before. All right, so because nothing disturbs our black hole, the geometry of the neighborhood of the black hole is approximately ADS Schwarzschild. The atmosphere does not get disturbed as well. It's the state of the atmosphere will also remain approximately thermal, and the horizon and the size of the black hole doesn't grow. This means that from the perspective of the operators in the vicinity of the black hole, the state looks identical in the final and the original moment. Correlation functions of atmosphere operators at the initial and final time slice are equal to each other, which means that whatever this V of H is, it has to be a modular symmetry. To be more precise, it has to be a modular symmetry in that within that code subspace that I can construct by acting with this atmosphere operator, this atmosphere fields phi on the background state. So there's a subspace that the observer has access to. The subspace of the CFT is the one obtained by acting with these atmosphere fields on the background state. There's whatever this unitary V that relates early and late time atmosphere operators is generated by the zero modes of this modular Hamiltonian projected on that subspace. A special zero mode is K itself, and Q alpha prime are everything else that I will not really discuss, because it's just the story works analogously there. Okay, so we argued that this has to be the form of this V, but we haven't argued for the physical interpretation of the coefficient that I said before. So let's try now to give a geometric argument, which I think makes it clear. All right, so imagine for now that you forget about the black hole, you have an ideal observer propagating in your space-time. And pick some kind of time slice. So here I picked the original time slice, but it could be any time slice along the trajectory of this guy, and focus in a little neighborhood around the word line. In that neighborhood around this word line, space-time looks approximately flat, which means that there's approximate local killing vectors which form a Poincare algebra. One of those killing vectors preserve the word line of the observer, and it's what we interpret as proper time, as the generator of proper time. Now, when we replace the observer with the black hole, what we essentially do is the following. We kind of choose some, some sufficiently large but not too large neighborhood tube around that word line, and we kind of remove it from the space-time diagram, and we replace the interior with the black hole geometry, which we now have to glue to the exterior space-time that we have left. And the gluing happens by demanding that the size of the transverse sphere is glued continuously along this fictitious boundary at this distance L, and that the original killing vector, the time-like killing vector of the ideal observer, gets glued to the Schwarzschild killing vector in the black hole spacetime. So with this argument, we learned that the Schwarzschild clock of the black hole keeps track of the proper time clock of the ideal observer. Now, of course, yeah. So to complete the argument, we need to now relate the Schwarzschild clock of the black hole to the modular clock on the boundary. But this essentially follows from the definition of essentially and the assumptions we made. So a way of thinking of the modular Hamiltonian in QFT is via this KMS operator. In particular, if I take the exponential of minus the modular Hamiltonian and compute its matrix element between two states obtained by acting with the atmosphere fields on the background state psi, is equal to this two-point function where the order of the operator has been exchanged. But now, because the atmosphere, as I said, is in local thermal equilibrium, nothing disturbs the atmosphere in this part of the argument. There's no infalling particles. We know that there's the KMS operator. We also know that the Euclidean Schwarzschild translation by an amount of 2 pi is also a KMS operator, because that's precisely the Euclidean, the weak rotation of the Schwarzschild time is precisely what serves as a thermal circle for the atmosphere close to the black hole. So this guy is also a KMS operator when acting on the atmosphere fields, and therefore the action of K and the action of this Schwarzschild time evolution is equivalent when acting on operators close to the black hole horizon. So this means that the proper time of the ideal observer is correlated with the Schwarzschild time of the Schwarzschild observer of the black hole, which is correlated to the modular time the variable conjugate to k. All right. This is it. That part of the argument. I have no idea how clear it was, but if there are any questions on this, now is the time.
Is the KMS operator unique?
Is the
Is that clear?
KMS operator unique? Up to symmetries of the state, I think yes.
Okay, thank you.
All right, I have an example which I think I will skip. You can make this, I will get back to it only if there are severe confusions on how this formalism works in practice. You can formulate everything precisely in black holes that propagate in ADS spacetime, and you can exactly decompose this unitary V into eigenoperators and rid of the proper time, which you expect from the geometric calculation. And then you can promote this to a story that also works for black holes that are accelerating in ADS, black holes that you can kick along the way, which allows you, by extension, which extends the validity of the proposal to any weakly curved ADS spacetime, to the extent that we can approximate the trajectory of the black hole in the Newtonian approximation. The prescription just works explicitly, as we saw in the paper. I will leave this only for the end if somebody has questions about it. I will just skip this example, hoping that the arguments were clear so far. I can't see your faces, so I have no idea the state that you're in. All right, so now we're going to switch gears, and now we're going to try to develop the formalism for the case where there are infalling particles. Clearly, we can't guarantee that our black hole will have an undisturbed journey. But the good thing about black holes is that they're detectors. They absorb particles, and the response is universal. All that happens, at least if you don't if you're not too ambitious and you don't want to propagate fields too far in the future, all that happens is that the black hole gets fatter. And what we have learned from the discussion of Schenker and Stanford, and of course all the discussions, is that if you want to glue together these two spacetimes of the slightly fatter black hole, then you have to do so by including a null shift, a relative shift between the two horizons, a shift which goes by the name of Sapir delay. And this could be a location-dependent shift. So the setup now is the following. We have, and we'll focus on a static black hole for the sake of the argument, but nothing changes for the case of moving black holes. You start at some original time slice, t equals 0. Phi naught here is some kind of near horizon operator, some atmosphere field. But now we act with a U of J, which creates some perturbative particles at a space-like distance from the atmosphere. And this, can propagate in space-time in some way, but eventually they will absorb by the black hole. They will make the black hole fatter, and then, of course, we have to glue these two spacetimes, as I said, and there is a relative shift between the two horizons. Now, what's important to remember is the way we dress the atmosphere operators at the early and the late time slice. We frame them to the local horizon, to the local ADS Schwarzschild frame in the neighborhood of the black hole at a given time. So this means that this guy over here at the early time will be at some geodesic distance from the RT surface, while this guy, the late time horizon operator, will be dressed to the shifted location of the horizon because of the absorption of the matter. So the proper time propagation up to transient effects, which are, however, confined within a little strip here of order beta around this infalling shell. The proper time will look like precisely this, approximately, will look approximately like this red trajectory that I'm drawing here. It originally propagates keeping the geodesic distance with the RT surface fixed. Then the matter cell goes through. There is some transient effects, but eventually all that remains, the persistent effect, is the shift that occurred because of this Shapiro delay. And propagation continues over here. All right, so this is what the exact proper time evolution looks like. This is what this unitary V of H, which is an input to our formalism between 0 and T, does. This is an input, this is an input, and this V describes precisely this process over here of this propagation with a superior delay. We would like now to relate this to the formalism that I was developing earlier. Well, in the previous discussion, we were using the modular flow to propagate in proper time. So you may ask, well, does it work in this case? So to address this, you construct the modular flow of the original atmosphere operator, which in this case will look something like this. The question of whether this operator is doing the job that the late time operator is supposed to do is the question of whether, by acting with this guy on my state, creates a state that has an order 1 overlap with the state that the precise operator which I have access to does on the state. Well, does it do so? If this is of order 1, then we have a decent reconstruction of this operator using modular flow. Well, but it turns out that this is very far from the truth, because if you if you just write out what this overlap is, it's an OTOC, where because this guy over here and this guy are separated in time, and they appear in this overlap in this kind of out of time ordering, which we know goes to 0 as you increase time, which means that this guy is a very bad reconstruction of what the late time operator is. However, the important thing is that this there is a nice way of understanding what this OTOC, another way of expressing the information in this OTOC, and this is by remembering that in the gravitational calculation, this is equal to the 2-point function with a relative shift between the operators, which is precisely what this shift here does. Where this delta x is precisely an exponentially growing thing in time, and it's a superior delay. So this means that the precise, and I want to emphasize this because this is kind of the essence, and you can see it here. The precise late time observable, which we have access to, differs from the modular flow operator by some amount of shift along the null direction, which is equal to the superior delay. So this means that so this means that in order to recover the proper time evolution, I simply need to take into account precisely this superior shift. So the modular flow effectively does something like this, and I need to include that shift in order to match the proper time evolution. And it's just a matter of writing things out explicitly to show that in order to accommodate for this superior shift, all you have to do is add to the modular flow that we were discussing earlier, this amount of scrambling mode, this contribution from the scrambling mode of K, where this G of 2 pi is simply the unitary conjugation of P minus J, which explicitly satisfies this, where this is the ANEC operator at a particular location along the horizon, and this precisely satisfies this commutator that I wrote out earlier. Now, and this kind of concludes this discussion. I hope that I argued somewhat convincingly to people other than myself and Daniel Jafferis that for as long as we wait at least a thermal time from the last absorption of a particle, and for as long as we don't wait more than a scrambling time after the absorption of the first particle, namely for as long as the proper time, but this is important, this is proper time in the frame of the black hole. For as long as the proper time I'm trying to measure is no longer than the scrambling time, then this is the form that the modular, that the proper time evolution has once expanded in eigenoperators of the modular Hamiltonian. So proper time and energy can be extracted from the coefficients of the corresponding modes. And that concludes, I hope, a decent explanation of this formula we discussed a few minutes ago. All right, so I'm exhausting my 20 minutes, I'm noticing right now, but I'm also done. I simply want to now get back to the conclusion. Am I granted 3.5 more minutes? Thanks. Thanks for the patience. All right, this is it. We developed some sort of story for extracting the experience of an observer, of an internal observer in setups where this concept is uncontroversial. So can we use that in order to try to address some aspect of this question I was asking in the beginning? What happens if I have a two-sided black hole? I introduce an observer on the right, and I want to now propagate this guy in proper time. Well, we don't. So how would we do this? We now understand that one way of introducing an observer is to choose a subsystem of the right CFT and entangle it with a reference. Ideally, we would form a black hole like what we did in our formalism, but I won't be explicit. This is supposed to be more like inspiration than an explicit resolution of the black hole interior. So the way we would do this in principle is that we would act with some kind of unitary that couples the right CFT and the reference, acting on the original Thermofield double of left and right and some kind of reference state of the reference. Roughly speaking, introducing this observer into the system entangled with our external reference will look like this. I'm not being explicit of what this OR will be, but this is what it's going to look like. And according to what I said, if you want to switch to the reference frame of the internal observer, what you have to do is trace out the reference and use the modular flow of the system to propagate things in proper time along this trajectory. Up to the caveat that if your black hole absorbs something, you need to also include the scrambling mode contributions, which we are not going to address here. This is closely related to the puzzle that has been giving us a headache, and it was originally suggested by Raphael, the frozen vacuum issue. I will not address this issue in this talk. But what we do know is that modular flow needs to be there. Well, in our opinion, interesting observation is that in this state, because of the left-right entanglement of this Thermofield double state, when you trace out the reference, the operator K, the modular flow, will not be a single-sided operator. It will be a two-sided object, namely it will not commute, well, it will couple the two sides. It will contain terms that couple left and right. This can actually be seen explicitly in a simple example like in SYK, where you can do this exactly. You can introduce a bunch of fermions and you can ask what is the modular Hamiltonian of this guy. And in the infinite temperature SYK, this will look like, this actually turns out to be the size operator of C and Streicher, which in the bulk looks like a sum of these horizon Einik operators, the near horizon symmetries. which of course are not single-sided objects. They couple the two sides. So while this is not at this stage of development an explicit reconstruction of the interior, because we don't have a diagnostic of whether matter was absorbed along the trajectory, this would be an important thing to understand, and we're working on it. I think that we do resolve this conceptual puzzle in that I've suggested a prescription for switching reference frames to the reference frame to the frame of an excitation that is internal into the system. And in this setup, we expect, because of the entanglement, the generator of the proper time of this excitation to precisely couple the two sides. So it's exactly what I was asking for originally. Can we derive the coupling that from some first principles? Can we derive the coupling that is relevant for propagating along this trajectory in some sort of framework that is understandable? All right, so this is it. Probing sub-ADS scales. I have a slide. I want to skip it so that I don't keep people waiting, and we can discuss this if there's interest. And I just want to end with the fact that we could have done exactly the same. Thing without entirely in a Wheeler-DeWitt patch. We didn't really need to propagate it in time. We could have asked what is the we could have had the early time atmosphere operators being on this kind of causal slice inside a Wheeler-DeWitt patch, and the final guys will be here, and the unitary that would relate them would precisely be related to the modular flow in exactly the same way that I explained. So this is kind of a notion of emergent time, which can, this is a buzzword, but it really follows from the entanglement between the ambient spacetime, the environment, and the degrees of freedom that make up the observer. And there's an interesting question of whether this, is a more general kind of framework for addressing this type of internal perspectives into other sorts of quantum mechanical systems that are supposed to describe gravity. And with that, I end and thank you for your patience and attention, and hope you enjoyed.
Okay, so maybe if somebody has some question for Lampros, even though we've already asked a lot, I think this is a good point to ask maybe some earlier questions after the conclusion.
Can I ask one?
Yes, please.
Sorry, if in the Marolf-Wall case, the one you just discussed a couple of slides ago, for the modular evolution to couple left and right requires that the reduced density matrix on left and reference not factorized, correct?
Yes, that's right. But this is exactly what happens in this situation when you introduce the observer like this.
Yeah, can you explain why that is?
Oh, why that is? Actually, if you write down exactly, okay, let me answer it by suggesting an exercise. Take the case of SYK, of two SYKs in the infinite temperature entangled state, which is the simplest kind of, it's not exactly the setup, but it's the simplest toy version of that setup, and apply precisely such the appropriate version of this unitary, and trace out the reference. And what you will see is that this is exactly what happens. What you end up getting is precisely this size operator, which is a two-sided guy.
Sorry, but the infinite temperature case is confusing because it is genuinely maximally entangled. So there is an exact version of monogamy which enforces that. Yeah, so the expectation, okay, so I don't think that switching to finite temperature changes that part of the conclusion. It will change this exact statement. K will not be the size operator exactly. It will probably have a contribution precisely from that sum of the two Modular Hamiltonians on the two sides, as you mentioned earlier, but the coupling will still be there. We have another example in the paper, which may be more illuminating. I find this a little bit more explicit, so I'm happy to discuss this in more detail, but I think if you sit down and try to ask that question, is the operator K in this obtained by tracing out the reference in this state?
coupling left and right, I think you would conclude that it does.
Okay, thank you.
If you conclude otherwise, send me an email.
Sure, thanks.
Can I ask a question about your final site?
Yeah, sure.
The last, yeah. So here in the cosmological case, you are imagining you're only focusing on a small causal diamond. Is that
here? So here I'm still okay. So in this setup, I'm still in ADS. I don't want to go very far from ADS because I feel uncomfortable.
this is ADS. Okay, so this is still spatial boundary.
Yeah. This is Wheeler DeWitt paths in ADS. I just wanted to illustrate the fact that so we didn't have to evolve in boundary time in order to this notion of internal time is in principle an independent kind of notion and could be formulated entirely in a setup where the asymptotic dynamical evolution doesn't play any role. So I don't have specific things to mention about cosmologies. But you know, this this could at least be some sort of framework, precisely because it doesn't depend on the existence of some kind of external evolution. Even if you have some sort of state describing the state of your de Sitter universe, you could have an emergent notion of internal time for certain types of probes. That's the extent of my comment, and
yeah, but there seems your modular operator need to acting on the whole system, apart from the reference system, right? Here, but in cosmology, I guess you only want to this modular operator acting on part of the space that you have access with. So you don't want to use an operator that describe like evolution in the whole space.
Yeah, so it's an interesting question exactly how this would be formulated in this context. I wanted to make a very high-level comment here that this may be a seed for some sort of notion of internal bulk time in other setups where an explicit asymptotic boundary evolution is not present. How exactly this will be formulated, I don't know. This is an interesting question and I haven't thought about it.
Okay, thank you.
Can I ask a question?
Yeah, sure.
So I think I understood the story about the Shapiro time delay, but let me just check. So I think what you're saying is you have an observable, which is the Shapiro time delay, that will detect the gravitational effect of particles that are falling across the horizon. Is that fair?
Yes, absolutely. That's fair.
Right. Now, what is it about the black hole setting that makes this? It would seem to me that I could have set up something similar at just empty ADS, for example. I could have focused on a particular set of modes, which, you know, follow null geodesics to a good approximation, and you know, I would have noticed that they detect a Shapiro time delay. If for example, I could have entangled my reference system with those modes. Why is it important that we do this with a black hole? And maybe related to this question, which part of your talk could not have been given in a language where we simply think of the black hole as the background itself? In other words, we have a black hole sitting in the center of ADS. We can always go to its best frame. And we can focus on particles that may be flying through its atmosphere, and we can ask whether we can detect a gravitational back reaction through a Shapiro time delay.
Mm-hmm. Okay, so first we have to agree on what question we want to ask. The question I wanted to ask here is I want to have a notion of a probe that will allow me to see the system from the inside. There's of course no fundamental restriction on what kind of detector you will come up with, right? You know, neither of us is a black hole, and we're still observers, and we build devices that are not black holes. The problem is that, you know, describing the general kind of well-behaved detector to probe ADS-CFT from the inside is an engineering problem, and we didn't want that. We want an idealization, some sort of universal type of probe that has a nice simple response to this type of, to observation of particles flying around. And that's exactly what the black hole did for us. You could have replaced it with some other kind of probe, but one of the things that the black hole was good for is that when it detects a particle, this gets imprinted in the Shapiro delays, which importantly, I can extract from this unitary that relates the early and late time atmosphere by simply extracting the scrambling mode contribution in this decomposition. So I can read it off. I can read it off in a way that doesn't require to know any details about the system, about the bulk. It's a purely boundary formulation of the problem. You have the unitary that relates the late and early atmosphere operators. You decompose it in this set of in this operator bases that are obtained from the modular Hamiltonian, and the coefficient of the exponentially growing contribution is a diagnostic of detection.
What would be different if I had instead entangled my reference system with a family of again, modes of some scalar field or whatever you were using in the atmosphere, the same kind of field, but without the black hole, just some modes that happen to be propagating, let's say, along a light-like direction across the bulk?
Yeah, so of course there would be, of course, the unitary that relates, you know, the observables between, you know, the initial and final moments will still encode this you know, this interaction that happened along the way. I just wouldn't know how to extract it from directly in the CFT without making reference to the boundary. Here, I knew exactly where to look for this effect. I knew that I had to, I mean, at least I explained to you that I had to look at these.
But you had to, sorry, I don't see the difference. I mean, to know what these modes were to start with in the case of the black hole, I mean, when you first entangled your reference system with the black hole, in those words, hidden in those words is the statement that you have some subsystem of the reference system that's entangled with the specific mode in the horizon that you're then following. I'm just throwing away the black hole part of that statement and doing it just for the field theory modes.
I may not be appreciating the question, because what I think that you're asking, and let me try to formulate your question to see if I'm understanding it. What I think you're asking is, could I have just chosen some subsystem, some, you know, a bunch of photons or, you know, whatever, a bunch of particles to entangle with the reference and use this as my probe? And the answer is yes. It's just that the effect of some other particle flying around and intersecting the probe's word line would have a much more complicated imprint in.
Why? So what I'm saying is take the exact same field that you're using in the atmosphere of the black hole. If the imprint of a particle flying through that atmosphere is simple, in other words, it doesn't really interact and it just leaves a Shapiro time delay. It interacts only gravitationally.
But this is
you clearly have such a scalar field available, and you could equally well consider the modes propagating through the bulk without the black hole.
Okay, it's important that the reason why the Shapiro delay is what matters is precisely because we have a black hole. It's the redshift of the near horizon geometry that extracts that gravitational interaction as the dominant contribution, and kind of everything else dies off because of quasi-normal decay. It's important that it's a black hole precisely because the only persistent effect that survives is not everything else that happened in between, but only the Shapiro delay.
But I mean, that's just a particular geometric setting. There's nothing special about this background. The point is that you can follow what the geodesics are doing, right? If you can do it when the black hole is present, you can do it without the black hole too. Either way, you're using what you know about how geodesics behave.
The particles I'm absorbing here are perturbative particles. The geodesic will not be affected by the propagation of these guys. The geodesic of the idea
is a statement that they are, right?
In the spacetime with, so let's compare two situations. One is the spacetime where I have some ideal observer following a trajectory. In this picture, if I act with this unitary that introduces some state excitation, these are perturbative particles. They don't affect the trajectory of this guy at leading order. these are, so at leading order in perturbation theory, the classical trajectory will stay the same, because these are, okay, but now I'm replacing this guy with a black hole.
No, that's not, so I want to stop you here.
Okay.
Because we're not, my point is that the work is being done by the modes of a free scalar field. It has nothing to do with a black hole, nor would it have anything to do with some massive observer that I might have been introduced. I wasn't meaning to introduce one. I was talking only about the modes of some free scalar field propagating through the space-time. They're doing all the work here. It doesn't really matter what space-time they're propagating through, so long as you know what it is. You can figure out things like Shapiro time delay.
Raphael, I disagree. And let me try to say it in a different way, where my disagreement is. The proper time evolution will, if something crosses paths with whatever probe you have, assuming it's a physical probe, if something crosses paths with your word line, will affect it in very many different ways. And the advantage that you get by having a black hole background is that all these transient effects die off exponentially in proper time. And the only things that survive are the Shapiro delays and the zero mode flow. If I didn't have that, the transient effects do not go away. The modular flow will be a non-local kind of evolution in time. So the modular flow of, after tracing out the reference, the modular flow generated by the system modular Hamiltonian will be a very non-local kind of thing. The reason why we are able to get away with it here is because all these non-local intermediate things die off exponentially because of the quasi-normal modes, and only the zero mode flow and the Shapiro delay persist at late times. And this is a feature that is only present when you have this black hole background along the word line that you want to propagate along. Maybe we can discuss this more, but it's very important here. The situation would be very complicated if you had any other type of probe without a nice universal kind of response to something that crosses paths with it.
Sorry, isn't this effect of everything being Shapiro time delay just a result of the probe and the incoming thing being very boosted with respect to each other? This happens at entanglement horizons as well, right? Like it happens at RT surfaces.
The probe and the infoiling and the particle are not relatively boosted with respect to each other. The late time atmosphere field and the infoiling excitation are relatively boosted with each other. It's not the probe that's boosted with it. The probe follows some geodesic in your space-time, and there's some guy that crosses paths. And the point is that it's the relative boost caused by the near horizon geometry that affects the atmosphere that is responsible for the Shapiro delay appearing in the late time atmosphere operators.
I think
type of, I don't consider very.
What Ronak is saying is that it would be exactly the same thing for a Rindler horizon.
That's correct. I don't know how I would use okay, that's correct, but I don't see how this relates to this story. Here, the black hole is my probe.
If you have control over these operators, in the case of where they correspond to a free scalar field in the atmosphere of a black hole, you must have the same amount of control over these operators if they're in the atmosphere of a Rindler horizon.
Yeah, the same thing would happen if I evolve in Rindler time. Then the same thing would happen in that case. It's just that I don't know how I would use a Rindler horizon as my probe in this case, right?
I think our point is that all the work is being done by having control over these operators. Whether we attach the word that there's something else that we call a probe is really not, I don't see how that enters any of the equations. Let me put it that way. That the math doesn't care about that word that we're attaching. Which I think is a sign that we didn't need it.
the final, yeah, the equations are indeed universal in that they only depend on the modular Hamiltonian after I trace out the reference and its eigenoperators. So yes, I agree with that. It's universal in that sense. The probe doesn't appear. I will insist that the expansion of this proper time flow would not, of the generator of the proper time would not admit this form had the probe not been a black hole. But I'm happy to debate longer. If there are other questions, maybe I should take those and then get back to that. And other, I think, look, this is an interesting question. I would very much like.
We have to leave something for the discussion.
Right, yeah, good, yes. Well, okay, I have nothing else in my life until the debate, so I'm here.
Yeah, no, I'm not, yeah, I don't know if I can handle that. But okay, any other questions for Lampros?
I want to ask my question about Kruskal time evolution again. What is the boundary dual of Kruskal time evolution? Because like you can see the effect that the left signal has on the right observer in Kruskal time evolution as well.
Yeah. It's important, Ronak. It's important that the Kruskal is an extension of the space-time behind the horizon, right? So it's kind of, when you're making that change of coordinate systems, you're kind of, you're choosing a way to extend the space-time behind the horizon, which I think all these arguments about firewalls and so on tells us that you should be careful about this type of extensions. So another way of motivating this work is to understand how do you concretely switch reference frames directly in the quantum mechanical system.
Right.
So we have not answered the question fully in the case of a guy falling inside the black hole because we haven't addressed Raphael's frozen vacuum issue at this point. Okay. And to be a little bit more explicit, we can detect particles that the guy on the left will send to the observer that by exciting the state I used to obtain the modular Hamiltonian, but I cannot detect particles that were already present in the state from which I derived the modular Hamiltonian.
Right.
So if the initial state had particles, I will not see them in this way, unless I have a way of another way of extracting these scrambling mode contributions. But I can only detect particles once excitations that were introduced on top of that state.
Right.
Of course, this is a drawback of this prescription. One needs to find a way of resolving this, and we're thinking about it. So in this case, the evolution of the atmosphere operators along that word line would correspond to this kind of modular flow plus scrambling mode flow that I was discussing.
Sorry, yeah, I'm on board with what you just said, but I was just thinking that, okay, let's take the specific example of a perturbed TFD, right? A TF, a Thermofield double, where, okay, and we all believe that this is a maximally extended black hole, two-sided black hole, right? So now Kruskal time evolution is just some large diffeomorphism of this geometry.
Okay.
And I believe that someone was shaking their head hard the last time I said it, so I might be wrong. But my understanding is that the generator of the large diffeomorphism is roughly h left plus h right.
Well, but that can't be, right?
Yes, that's what's confusing me.
Well, okay. But doesn't that mean that that's just not the case? Because that wouldn't propagate you behind the horizon, right?
Okay.
In fact, according to what according to this little discussion I had over here, I would say that the generator along the wordline evolution along such a trajectory would necessarily have contributions between the of these Einik operators, which are inherently two-sided. They don't preserve the operator algebra on a single side. They move things along the horizon and can take things, operators from here to there and so on.
Okay.
So now we can discuss this more, but I think. Yeah.
No, sure. I'll check this again then. Yeah. Thanks.